Welcome back. Today's goal of this lecture. Today I will see what is the actual differentiability in complex analysis. In my previous video I have seen what is the topology on complex analysis. This is also part of topology. What is the differentiability I will see. My previous video I had seen what is the continuity, open ball. Also I had seen differentiability. I had seen differentiability is local property. Today I will discuss differentiability briefly because whole complex analysis actually depends on differentiability. The differentiability in complex analysis. Let D be a subset of complex number and A belongs to C. Then consider one ball B of air with center A and radius R which contain the set D, and these ball for some are greater than 0. Now consider one function f from D to C be a function. Then derivative of f at a point A is defined to be limit h tends to 0 f of a plus h minus f of a h over h. If this limit exists, then we say that f is differentiable at a point A, and if the limit does not exist, then f is not differentiable at a point A. Now we will see f which is defined from complex number to complex number. I will see fz equal to z real z. This is only differentiable when z equal to 0. Otherwise, this is not differentiable. I will see this example. For this, consider z be arbitrary number in the complex plane. Then, limit h tends to 0 by the definition of derivative is f of z plus h minus f of z over h. And this would be limit h tends to 0 z plus h real z plus h minus z real z over h. Then this value would be limit h tends to 0 z real z plus z real h plus h real z plus h real h minus z real z over h. Now this would be cancelled. Then this value would be limit h tends to 0 z real h plus h real z plus h real h over h. Then this value would be limit h tends to 0 z real h over h plus limit h tends to 0 real z plus limit h tends to 0 real h. Why does not exist? Because h goes to 0 means h goes to indifferent part. If we consider through purely imaginary number, h goes to through purely imaginary number, then obviously real h is equal to 0. And real h equal to 0 means real h over h equal to 0 when h goes to 0. Okay? And when h goes to 0 through real number, then consider real h equal to h. That implies real h over h equal to 1 as h goes to 0. Therefore, here the value, I have got the value 0 and here I have got the value 1. For different part, I have got two different value. So limit a is goes to 0, z real s over s does not exist. If z equal to 0, then z real s over s always equal to 0 as s tends to 0. Thus, limit s goes to 0 real z and limit s goes to 0 real s always be exist. So, we can tell only f is differentiable at the point z equal to 0 and f prime 0 equal to 0. Now I will see fz equal to mod z square. Similar to before, this is only differentiable when only z equal to 0. S means obviously small increment. So consider S as a del z. Then limit del z tends to 0. Here I have considered S as del z. F of z plus delta z minus f of z over del z. Then this value would be limit delta z tends to 0, absolute value of z plus delta z whole square minus z square over delta z. Then this value would be limit delta z tends to 0, z plus delta z times z bar plus delta z minus z times z bar over delta z. Then this value would be limit delta z goes to 0, z times z bar plus, sorry, here also z bar, delta z bar, delta z times z bar plus delta z bar times delta z minus z bar over delta z. Then this value would be, just cancel, then this value would be limit delta z tends to 0, z times delta z over delta z here bar plus limit delta z tends to 0, z bar plus limit delta z tends to 0, delta z bar. To before, limit delta z tends to 0, z bar and limit delta z tends to 0, delta z bar always exists. Only this part not equal to, when z not equal to 0 does not exist. If z not equal to 0, then delta z bar over delta z means delta x minus I delta y over delta x plus I delta y along the axis, along x axis means obviously y equal to 0, then delta z bar over delta z means obviously delta x over delta x whose value would be 1, and along y axis obviously x equal delta x equal to 0, then this value would be minus I delta y over I delta y, and this value would be minus 1. Notice, similar to before, along x-axis the value of the limit is 1 and along y-axis the value of the limit is minus 1. Since for different value of delta z, the limiting value is different, so the function mod z square is not differentiable when z not equal to 0. But when z equal to 0, then obviously this value would be tends to 0. So the function fz equal to mod z square only differentiable at z equal to 0. Then f prime 0 also would be, the value would be equal to 0. Now consider one function f which is defined from R2 to R2. Then differentiability in terms of matrix, and differentiability of a function is denoted as in terms of a matrix. Then differentiability of a point is actually linear approximation of any function, and differentiability at a point AB would be the matrix, the Jacobian matrix del u del x, del u del y, del v del x, del v del y at the point AB. And differentiability means all partial derivative exist and continuous at that point, because differentiability means this matrix. So this means always all partial derivative exist and continuous at this point. Now we all of us know differentiability at a point z equal to x plus iy means f prime z equal to limit h tends to 0 f of z plus h minus f of z over h. Here h goes to 0 means through different one it can purely imaginary number or it can be purely real axis. When h approaches through real axis, then f of z plus h minus f of z over h means f of z means x plus y, x plus iy plus h minus z means f of x plus iy over h, and f of x plus iy plus h means u x plus h comma y plus I v x plus h comma y, and f of x plus y means this is u xy plus I v xy over s. Okay, and obviously this means limit h goes to 0, h belongs to R, u x plus x comma y minus u xy over h plus I times limit h goes to 0, h belongs to R, v x plus h comma y minus v of xy over h. And this part means obviously del u del x over x comma y, and this part means del v del x at the point x comma y. Okay, therefore f prime z equal to del u del x at the point x comma y and plus I del v del x at the point x comma y when a goes to through real axis, and when a goes to 0 through purely imaginary number means a is equal to I k where k belongs to R, then f prime 0 equal to limit h goes to 0 f of z plus h minus f of z over h. Here I have considered h is through purely imaginary number. So I have considered h equal to ik. Then limit a is goes to 0 means since I have considered a is equal to ik, therefore limit ik goes to 0 f of z plus ik minus f of z over ik, and this value would be equal to limit k goes to 0, k belongs to R, u x comma y plus k minus u xy over ik plus I times limit k goes to 0 v of x comma y plus k minus v of xy over ik. Now cancel this part, then this value would be limit k goes to 0 and k belongs to R, u of x comma y plus k minus u xy over ik plus limit k goes to 0 and k belongs to R, v of x comma y plus k minus v of xy over k, and this value is equal to minus I times del u del y at the point xy plus del v del y at the point xy, then f prime z equal to this. So if we consider this part and this part, then since from above we have got f prime z equal to del u del x at the point xy plus I times del v del x at the point xy, then that implies del u del x equal to del v del y and del v del x equal to minus del u del y, here at the point xy, here also at the point xy. Therefore, and these two equations are called Cauchy-Riemann equation. So when the function is differentiable at z equal to x plus iy, then real and imaginary part always would be satisfy the Cauchy-Riemann equation. I hope my all viewers have understood. This is very useful result. When a function is differentiable, then always satisfy the shared equation. Shared equation means del u del x equal to del v del y and del v del x equal to minus del u del y. Sorry, here y not x. For example, fz equal to z cube. Then limit h tends to 0 f of z plus h minus f of z over h. This value would be 3z square. And f of z means obviously x cube minus 3xy whole square plus I times 3x square y minus y cube, where z equal to x plus iy. Then this part is u and this part be v. This is u plus iv, where u equal to x cube minus 3xy square and v equal to 3x square y minus y cube. Then del u del x equal to 3x square minus 3y square and del v del x equal to 6xy. Del u del y equal to minus 6xy and del v del y equal to 3x square minus 3y square. So, function is differentiable, also is satisfy the shared equation del u del x equal to del v del y and del u del y equal to minus del v del x. So, when a function is differentiable, then always is satisfy the CR equation, but converse not true. Means CR equation satisfied, this does not always imply function be differentiable. As for example, if you consider fz equal to x cube times 1 plus I minus y cube times 1 minus y over x square plus y square. This means x cube minus y cube plus over x square plus y square plus I times x cube plus y cube over x square plus y square. And this part is uxy part and this part is vxy. Then del u del x means limit x goes to 0 ux0 minus u00 over x, and this value is 1. And del u del y means at the point 0 limit y tends to 0 u0y minus u00 over y, and this value is here minus y cube over y square over y means this value is minus y. And del u del v del x means del x would be 1 and del v del y also would be plus 1. So del u del x equal to del u del y and del v del x equal to minus del u del x equal to del v del y and del v del x equal to minus del u del y. So this satisfy this equation, satisfy the CR equation. But to check differentiability at z equal to 0, the formula is limit z goes to 0 f of z minus f of 0 over z minus 0. Now put the value of the function. After calculating, this value would be 1 plus I times x cube plus I y cube over x square plus y square times x plus iy. Now multiply this equation by its conjugate. Then this value would be, since z tends to 0, that means limit x goes to 0 and y goes to 0, 1 plus I times x cube plus I y cube times x minus iy over x square plus y square to the power whole square. Now put y equal to mx and x goes to 0. Then this value would be limit x goes to 0, 1 plus I. When put y equal to mx, then this value would be x cube plus I mq x cube minus x minus I mx over x square plus m square x square to the power whole square. And this value would be 1 plus I times 1 minus ix times 1 plus I m cube over 1 plus m square to the power whole square. Notice, for different value of m, I will get different result. So this function is not differentiable at the point z equal to z 0. But at the point z equal to 0, 0, the function has satisfied the CR equation. Means when a function be differentiable, then always it satisfies the CR equation, but converse not true. CR equation satisfied, that does not always imply the function be differentiable. Now I have seen f is differentiable at a point a plus ib means obviously f is differentiable at a point ab, and df, which is the linear approximation of the function near the point a plus ib. df at the point ab means derivative of this function would be del u del x, del u del y, del v del x, del v del y. And since function is differentiable, that means it satisfies the CR equation. Then this would be del u del x, del u del y, del v del x means minus del u del y, del v del y means del u del x. And this value would be obviously del u del x whole square plus del u del y whole square. This derivative at the point AB. So, Jacobian of this function at the point AB is del u del x whole square plus del u del y whole square. A prime a plus ib means del u del x plus I del v del x, and del v del x means obviously del u del y x minus I del u del y. This is the a prime a plus ib at the point AB, and absolute value of a prime a plus ib, this modulus whole square would be del u del x whole square plus del u del y whole square at the point A, B. df is the linear approximation of a function near the point A plus ib, and if you take small increment of A plus ib at the point alpha 1 plus I alpha 2, then df here the small increment of A plus ib is alpha 1 alpha 2. Alpha 1 plus I alpha 2 means this, and this is equal to determine del u del x del u del y minus del u del y at the point AB alpha 1 alpha 2. His value would be alpha 1 del u del x plus alpha 2 del u del y plus I times minus alpha 1 del u del y plus alpha 2 del u del x. If you write this as component wise, then this would be alpha 1 del u del x plus alpha 2 del u del y. Here would be minus alpha 1 del u del x plus alpha 2 del u del y. Sorry, here not x, here minus alpha 1 del u del y plus alpha 2 del u del x. This value be the derivative of this function at the point AB, and if we increment A plus IB at the point alpha 1 plus I alpha 2, then this would be the value. Is actually equal to alpha 1 square plus alpha 2 square del u del x whole square plus del u del y whole square, and this value is mod alpha square A prime A plus IB whole square. Okay, I hope my all viewers have understood this is. Today I will stop here. In my next video I will discuss what is the analytic function in the complex analysis. In my next video I will discuss this topic elaborately. But to understand analytic function elaborately, first you have to learn what is the differentiability in complex analysis. If you know the differentiability of complex analysis CR equation, then you can understand what is the analytic function in briefly. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.